Section 3.3, Piecewise-Defined Functions. Our goals for this section is to first define a piecewise-defined function. We want to be able to sketch a piecewise-defined function, write piecewise-defined functions that model graphs, and talk about how to use a graphing calculator to graph a piecewise-defined function. So, what is a piecewise-defined function? A piecewise-defined function is a function that is defined by different formulas for different parts of their domain. So here's a common example. A cellular phone carrier offers a monthly texting plan that includes 500 texts for $5 per month. For each additional text beyond 500, the user will be charged 10 cents. Alright, so we want to be able to write a piecewise-defined function that models the monthly cost for texting under this plan and sketch the function. Alright, so let's think about this. If you have 0 texts, you're going to be charged $5. 100 texts, still $5. All the way up to 500 texts, you're going to be charged $5 for the month. Alright, so our function, let's see. If my x value, we can't have a negative number of texts. If my x value is between 0 and 500, the cost is 5. And we'll put a little if here. Now, what if my x value is above 500? I'd still have the initial $5, but I'd have to increase that by 10 cents for each additional text. So my slope would be 10 cents, which is $0.1, and for each additional above 500, so x minus 500 would be in quantity. So notice, if I have, think about this. If x is 600, that means I have 100 additional, right? And notice that 600 minus 500 does give me the 100 additional. Alright, so here is a piecewise defined function. Alright, so now let's sketch it on this. We don't really have a grid, but let's say my scale on the x-axis is by hundreds. So there's 500, 6, 7, 8, there's 900, okay? And on the y-axis, let's use a scale of dollars. So let's see. 1, 2, 3, 4, there's 5. 6, 7, 8, 9, there's 10, etc. Alright, so for the first, now again, if we have 0 text, it would still be $5. But then it holds steady until we get to 500 texts. And then the price increases. Alright, so if x was 600, that means we'd have 100 additional texts, so I'd have 5 plus so if x is 600, we'd have 5 plus 0.1 times 100, and so that would be 5 plus 10, which is 15. So 600 texts jumps all the way up to $15, and it would continue upward from there. And it would continue upward from there. Alright, so there's a graph that represents this situation, that models this situation. Alright, so let's graph the function. this is a piecewise defined function. F of x is equal to negative 3x plus 1 if x is greater than or equal to 2, and it's equal to 1/2 x plus 3 if x is less than 2. So one thing that I sort of like to do to help students figure this out is I immediately draw a boundary where things change. So notice things are changing at x equals 2. So I'm just going to put a vertical line at x equals 2 to remind me that things change at x equals 2. All right. I like to use a couple of different colors. So I'm going to draw negative 3x plus 1 in blue. I'm going to draw 1/2 x plus 3 in red. So now the technique that I'm going to use here is I'm going to draw both of the curves, lines in this case, and then I'm going to erase appropriately. All right, so negative 3x plus 1 is a line with y-intercept of 1 and a slope of negative 3. All right, so I've drawn a few points there, and drawing this line. All right, so there's that line. And then y equals 1/2 x plus 3 is a line with a y-intercept of 3 and a slope of 1/2. So there's a few points on that line in red, and drawing that line. All right, but that's not the graph of the function. For one thing, we have too many points. We can't graph this. This isn't a function because it doesn't pass that vertical line test. All right, so let's remember something now. It's only defined by negative 3x plus 1 if x is greater than 2. So we only want the blue to the right. So I'm going to erase the blue on the left of that boundary. Similarly, we want red to the right. So I'm going to we want red to the left, less than 2. So I'm going to erase all of the red on the right. Now I'm also going to erase my boundary. All right, and then we have one more thing to take care of. We have to put some endpoints on these. So since this was an or equal to, this point at the boundary of the blue line gets a solid point. And since this was a strictly less than, this point gets an open point. And there's the graph for the function. Here's another example, a little bit more complicated. We have f of x is the absolute value of x minus 2 if x is less than 4, and f of x is equal to the square root of x if x is greater than or equal to 4. Again, let me draw in my boundary at x equals 4, because that's where things change. I'll again use blue and red here. All right, so blue for the absolute value of x minus 2, well, that's just absolute value of x shifted 2 to the right. All right, so we would have, there's a few points on the curve. And we have the absolute value function. And then we have an absolute value function in red. I'm sorry, square root function in red. So let's see, that's 0.0114293. And we get that. All right, so now let's see. We want the absolute value function for x is less than 4, so we want blue to the left of 4. All right, so I'm going to erase all of the blue that's to the right. All right, and we want square root of x if x is greater than or equal to 4, so red to the right. So let me erase all of the red that's on the left of that boundary. And I'll erase the boundary itself while I'm at it. All right, now notice in this case, both of those that they connected, and they connected specifically at this point 4, 2. So we don't need an open or close, it's just a simple connection, okay? It's only when they don't connect that we need to worry about whether we put an open point or a close point. All right, let's go in the other direction. We need to find a piecewise defined function that models this graph. All right, so first thing I notice is that things change right here at x equals -2. Okay, so that's important. So when I define my function, it's going to have two pieces. Now let's see, we have an open point and a closed point, so it's going to be something if x is less than -2. It's going to be something else if x is greater than or equal to -2. All right, so let's look at that first part. And I'll just think of this in blue, okay? So I'll work that line in blue. Let's see what we can do here. We have a couple of points. We know it looks like a line, so let's use a linear function. There's 2 points, -4, 3, and -3, 1. Hey, we can find the slope, right? M equals 1 minus 3 over -3 minus 4, minus -4, sorry about that. So that would be -2 over 1, which is -2. And so then we can use that and one of the points. Let's see, y minus 3 is equal to -2 by x minus -4. Y minus 3 is -2 by x plus 4. Y minus 3 is -2x minus 8. And adding 3, y equals -2x minus 5. So f of x is 2x minus 5 if x is less than -2. Now we're going to do something similar with the other piece. Let's erase all of our... I'm going to erase my work because I'm running out of room. I'll work in red for the second line here. Let's find 2 nice points. We could use this starting point. What is that? -2, -4. Use that point. And hey, it goes through 0, 2. That's nice, because that's the y-intercept, and if it's linear, that makes life a lot easier. M equals 2 minus -4 over 0 minus -2, and that is 6 over 2, which is 3. And since we have the b value of 2, that means y equals 3x plus 2. So then the function is 3x plus 2 if x is greater than or equal to -2. So there's the piecewise defined function that models that graph. All right, here's another example. We want to find a piecewise defined function that models this graph. This one's a little bit tougher. It appears that we have maybe an x square function and then an absolute value function with some transformations. So let's figure this out. And notice that it changes at -4. Alright, so when I'm writing my function, I have f of x equals something if x is less than or equal to -4, solid point, or equal to. And something else if x is greater than -4. Alright, from the looks of things here, for the x square, it looks like it's been shifted left 4 and down 2. So let's start there by saying that that function is a by x plus 4 square minus 2. We have another point right there at -5, -1. So then we would have -1 is a by -5 plus 4 square minus 2. -1 is a by -1 square minus 2. -1 squared is 1, so -1 is equal to a minus 2. Add 2 to both sides, and a is 1. So the first part of the function is 1 times x plus 4 square minus 2. We normally don't write that 1 out front. Alright, so there's that first part. Now the second part is an absolute value function, and again let me erase this so I have some room to work. And it appears that my center has been moved left 3 and down 2. So let's start with that. We have our f of x is again some a value times the absolute value of x plus 3 minus 2. Where's another nice point? Let's use this point right here at -2, -3. I would have -3 is equal to a times the absolute value of -2 plus 3 minus 2. So -3 is equal to a times the absolute value of 1 minus 2. The absolute value of 1 is 1, so I have -3 is equal to a minus 2. Adding 2 to both sides, a is -1. So then the second part of the function is -1 absolute value x plus 3 minus 2. And so there is a piecewise function that models this graph. Alright, let's finish this off with an application. Jill, a junior high school student, decides to take a summer babysitting job to save money for a car. The neighbor would rather have Jill babysit for the entire week rather than having 2 different sitters. Therefore, the neighbor has agreed to pay Jill $8 per hour if she works up to 15 hours. If Jill decides to work more than 15 hours to a maximum of 40 hours per week, she will receive $10 an hour plus a weekly bonus of $40. Alright, so we're asked to first write a piecewise defined function that represents the weekly salary S for X hours. All right, so we have S of X equals, now let's see, up to 15 hours per week. Well, let's make the assumption that she can't work less than 0 hours. So if we have 0 less than or equal to X less than or equal to 15. So from 0 to 15 hours, her pay is $8 per hour, 8x. However, if Jill decides to work more than 15 hours to a maximum of 40 hours, so if 15 is less than or equal to x is That would be strictly greater than 15, less than or equal to 40. Then her pay is $10 per hour plus a weekly bonus of $40. So there's our piecewise defined function. All right, we're asked to now graph the function with the graphing calculator. We're going to state the window and label the axes. Now, graphing piecewise defined functions on the graphing calculator is a little tricky. All right, so let's see this. Here's how it works. We're going to use test and logic functions within the calculator to do this for us. So here's how I do this. First, in parentheses, I'm going to put the first function, 8x. I'm going to multiply it by a conditional statement. All right, so I put some parentheses. Now, the conditional statement was x was less than 0 and x was less than 15. I'm sorry, x was greater than 0 and less than 15. So x, now go to the test, which is the second function of the math key. I want x to be greater than 0. Now I need to use the logical symbol AND, which is also under the test, under logic, and x is less than 15. Test is less than 15. I'm going to close that off. So now that's going to give me the first part. Now what I'm going to do is now add on to it the second part. Plus, in parentheses, 10x plus 40. Close that off. Multiply that by x is greater than 15 and x is less than 40. So now what happens here? What the calculator does is it chooses x values, and it's checking this thing first. This x is greater than 0 and x is less than 15. If that comes back as a true statement, then that quantity becomes a 1. If that value comes back as false, it becomes a 0. True goes to 1, false goes to 0. And so whenever that statement is false, we are now multiplying by 0. Same thing here. So now let's think. If I chose a value of x, say 10, for 10 hours, this first part would come back as true, and the second part would come back as false. And so what happens is, it only uses the first part, not the second part. So that's how it's working. All right, so now we have this in our calculator. Let's actually graph it. So let's think of a reasonable window to use. All right, our hours, our x values go from 0 hours to 40 hours. Just to make the graph look nice, let's go from -5 hours, I know that doesn't make any sense, to 45 hours, and let's use a scale of 5s. And for our y values, that's dollars. The minimum is $0. Again, we'll go a little bit less. How about we go to -$10? And a maximum amount. Well, if she works the entire 40 hours, that would be 10 times 40 is 400 plus 40 is 440. Let's just go up to 450 for the maximum. And I'll use a scale of 50s. All right, let's graph it. So now we get some little features here that are part of the graph. So let me copy this over to our screen and annotate it a little bit. All right, so there's our graph. Now, this is our x, and this is our s of x, And let's put a little bit of scale. We said that each mark was 5 hours. So this is 5, 10, 15 hours. And each mark on the y-axis was 50. So there's 50, 100, 150. All right. So now what happens is we should have a solid point here, an open point here, and a solid point here. And these are just, sort of artifacts from the programming. Those parts shouldn't be in there at all. So there's the graph, and there's a graph we can use. Oh, and the window was what, negative 10 to 45 by negative 10, or sorry, it was negative 5 to 45. And negative 10 to, what, 500, I think. Or it was 450, something, I don't remember exactly. So there's our viewing window. How much will Jill earn if she works 35 hours? So if she works 35 hours, then the function would be defined by the second rule, which would say it would be $10 times the number of hours plus the bonus of $40. And so that's 350 plus 40, that's 390. So we have the point 35, 390. Let's label that point on the graph. All right, so let's see. This mark would be 35, so this point roughly up here would be 35, 390. If Jill were to earn $112, how many hours would she have worked? Find your answer algebraically. So we need the output to be 112. Well, which rule do we follow? Let's see what happens. If we set the 112 equal to 8x, that was the first part of the rule, then we would have, 112 divided by 8 is 14. X equals 14. If we set the 112 equal to 10x plus 40, then we would have had, 72 equals 10x, and x equals 7.2. Now, remember the first rule was defined, the 8x was defined for 0 is less than or equal to x is less than or equal to 15. And 14 fits in here, right? 14 fits in here. The second rule was defined for 15 is less than x is less than or equal to 40. And 7.2 does not fit in there. So that can't happen. So the point, she would have worked 14 hours. And the point would have been 14, 112. Let's mark that point on the graph. All right, so 14, 112 would be, about here. This point is 14, 112. All right, and that concludes the presentation for section 3.3.